Hello all. Thank you all for joining in different time zones. I know we are joining from USA, Europe, India. Sorry if I missed somewhere. And we are very happy to have Fred Calef here to give us a talk on the Multi-Mission Geographic Information System, MMGIS. So, nearly all missions require spatial awareness and an ability to combine results from different multiple data sets and data sources in their proper geospatial context. The NASA Advanced Multi-Mission Operation System developed the Multi-Mission GIS as a free and open source software for geospatial web-based application for science operations as part of a mission's planetary spatial data infrastructure. MMGIS provides spatial display and query capability utilizing open source vector, GeoJSON, and raster like GeoTIFF, DEM Tiles formats in 2D, 3D, and in situ views. Initially deployed for Mars rover surface operations, MSL Insight Mars 2020, the software has been improved for Earth and Moon like lunar Viper missions. We will discuss the latest, Fred will discuss the latest tools and unique ways in which we can use the open formats for geospatial science operations on a variety of missions. Our speaker, Fred Calef, is a geologist and science system engineer at NASA JPL. He is generated geospatial data sets and analysis for landing a site selection for MSL, Insight, Mars 2020, and Mars Sample Written. In addition, he is the lead mapping specialist on the Perseverance rover, the keeper of the maps for Curiosity, and the PA for MMGIS. We welcome Fred to tell us more about MMGIS, and we're eager to learn. Fred, you're muted.
Oh, there we go. I am no longer muted. Does that look good for everyone?
Yes.
Okay, fantastic. All right. Let me just see if I can move things around my screen so that it's annoying. Okay. I have too many slides and not enough time. So I'm gonna move right along. Okay. So when I came to JPL, was my first time getting involved in missions, but all my previous work, whether I was working for a transportation agency or a local government institute or a university, is like whenever we have a project, when we have a mission, ultimately it's always about location. Where are you? Decision making happens because you need to know where you are, where you're going to be, and then what are you going to do. So you need a map essentially to operate missions at many levels, even though we talk about power and energy and data volumes, but you got to know where you are. And so the GIS systems, of course, are this way that we can do that, because you're bringing in different data formats from different systems, and you can make things easier for people. And NASA wants to transform to open science, right? And they call it a 5-year journey. We started that journey a while ago, and I'm sure a lot of people here have also done the same thing. And the goals of having open science are important, but how do you do it, right? And to me, open science, it begins with open software and open data sets. But I think the key part is also open operations, so that you know how to put the data sets into the hands of people and make them useful. And that's really my goal with MMGIS, because you have, spacecraft. They can be orbital, they can be in situ on the surface, they can be, aerial now. They have lots of instruments, sometimes, 5 instruments, 10 instruments on the same spacecraft, and they collect data. And there's a variety of coordinate systems that you have to go through, especially for rovers. You go from an instrument coordinate system to an arm coordinate system to the rover coordinate system, then to the global coordinate system, right? And when people collect data, they like, oh, this is a great result, look, we found this high silica, or we found a lot of manganese. And the next question is almost always, where is it? And then where is this measurement compared to the previous time we saw this high value? Or why are all the other values low and where are they? So where becomes very important. And it doesn't matter whether you're a geochemist or a geophysicist or a geomorphologist. If you're a mission scientist, you want to know where things are. And I like to say time equals science. We want scientists spending more time being able to see their data contextually where it is, as opposed to trying to figure out, the 5 different coordinate systems and all the mapping part, which they're not specialists of. So I can tell you what MMGIS is, but really the people who have used our software really get what MMGIS is. It's a basis for preparing for science operations. It can be deployed with ease. It's made for just for a geographically distributed group of scientists. It democratizes data access. People using it for scientific papers. They're allows the public to see and follow mission as they go along. It's used for long range planning, et cetera, et cetera. So it solves this part of once you get the data, what do you do with it? Which is usually the part where missions kind of stop and they leave it on the scientists to figure that out. But we're working on making this actually part of the mission so that you can have the interval loop of we planned some data, we collected it, now we got results. Now, what do we want to do next, right? So this decision support, I think, is very important in terms of MMGIS, in terms of mapping as part of that decision process. So what does MMGIS look like? It is a web-based application, and we basically, as a geologist, right, I want to see things from all different views. So we have a traditional top-down 2D view, which is how MMGIS starts. But we also have side panels that you can actually open up a 3D view and an in-situ view, so that you can see data, from above, from different angles, and on the ground. And they can be, data at different scales, and combining different data sets and then different tools that we can interoperate. So on the kind of the technical side, MMGIS is a web-based service. It's running off of Node and incorporates Leaflet as its main 2D mapping library. And then we also use 3JS for 3D and some other graphing capabilities. And then, all JavaScript and CSS and what have you, HTML. Behind that is also GDAL, which we use for, gathering some data, tiling data, doing some data manipulations, and Python, of course, that works with that for some of the background automation. And then we connect to open sources. So we do, MMGIS does connect to a Postgres, PostGIS database, supports spatial operations, some of its drawing tools, but we can directly point to GeoJSON or Mapbox vector tiles in vector land, and then in rasters, we're mostly using TMS tiles. And also, we can point to WMS and WTMS services. And typically we're using GeoTips as kind of our conversion format, but really could be any raster spatial format. And on the top right, what you're seeing is just the configuration page. So it's so make it easier to kind of set up a mission, figure out the layers, what tools you want on, what properties. And again, this is open source. It's out on GitHub, and it is under Apache 2.0 license. Okay, so what does it look like? So this is going to be a little bit fast, just because I wanted to fit all that in a short amount of time. So this is showing how we can turn on different layers, whether they're chemistry or geology or what have you. Make them apparent. We can get some information by mousing over and get actually the kind of either get raw values or values from a legend. And then we're going to just show off a couple of tools. Here's our measure tool, which allows to do profiles and measure distances and angles, which are often used a lot by mission people to figure out where things are. So now we're just zooming in and showing off that we can click on a location and see data in situ. So this is actually a photosphere. And just by clicking points, you're rapidly being able to look down onto the surface from the rover's point of view and start to see what the surface is like. And this is just showing, it's not also raster, it's also vector. So here are a bunch of targets that are located near the rover. Here's the footprint of the rover. So you can just kind of see the names of those. So you can investigate, what targets you've done. And then you look at it in 3D. And importantly to know, this isn't like we made 3D data, and then we have 2D data, and then we have in situ data. The data that's used for 2D, the tiling and the vectors, are also used in the 3D itself. Actually, hold on. Let me just stop this for a second. This is all kind of making my head hurt. Okay, so like the data we're using for the map is just reused again for the 3D. So we actually, later I'll talk about how we create elevation data. We use it on the fly to create a mesh, but it's creating a mesh from the tile. So we're very efficient in terms of our data use in that way. Okay. So just to show off a few different things, you know, we're working on, you know, we really don't care what the shape of your planet is. If it's spherical, we're kind of good. So top left is just showing off our viewshed tool on Jezero Crater. To the right is Earth, actually looking at time series data for geodetic stations. On the bottom left is Mercury, just kind of browsing around and looking at image footprints. And to the right is a tiger stripe on Enceladus. So we really don't care where the data is coming from. As long as it's got some spatial component, we can use the same tool in the exact same way. So this is kind of sort of like the graphing tool up on the right, looking at time series. This is native, this is like core MMGIS without doing any spatial changes. Otherwise, it's just changing like what's the radius of the planet, and then it just works. Okay. And it's as sometimes, you know, you make a tool at your location and the tool gets used within your location, it doesn't escape. Not so for MMGIS. It's being used by NASA Ames to support the Lunar Viper mission. It's been used by Scripps to do that Earth science time series data. Obviously we use it at JPL a lot. ESA's also adopted it when they did some geologic mapping for the Rosalind Franklin rover, because some of their team members who were on M20 did geologic mapping and they saw us doing it, and they want to do it themselves for their mission Oxia Planum. And then JSC actually used it a little bit in the early days of doing some EVA testing out at SP Crater in Arizona for doing field work, to see how like having an actual map part of flight operations, how they could integrate it into their work. But also importantly, it's not just on many missions at different centers. It's also each mission is contributing back to the core software. So we do our best to not clone and own, right? Like you take code, you pull it, and you know, you bring it down and you modify it and you make it your own. And the tools that you make never go back into the core. Our missions were always pushing to push new tools back into the core. So collaboration tools that started with Msl got made to 2020, then got pushed into Lunar Viper. Mars sample return needed a line of sight analysis tool, then that could be used back for helicopter, and it can go back to Mars 2020 and it goes back to all the missions. Time aware layers were built in for time support, was built in for Lunar Viper, and then Emit picked that up and then expanded upon it. So that's really what we push. We try to remove the technical debt when we have tools being implemented, and certainly being open source helps us in that manner to kind of keep building on the core software and not just splintering it off into five or 10 different versions. And you know, it's not just for operations. We actually do push this to the public. So the same software is just using to serve the Where's the Rover websites for both Perseverance and I said Opportunity, that was bad, for Perseverance and Curiosity, so they can, you know, track rover progress. And we even have you know, people who, you know, when they want to access like where the rover is programmatically, they can actually pull the GeoJSON of all the rover waypoints and the traverses and the sample locations for their own deeds. And when you see that in some applications, they're actually yanking the data straight from us, and that's great. That's exactly what we want. Like, I don't want to make all these cool tools. Like, people should be able to use them and the data itself. So some of the things that kind of spawned out of MMGIS, well, we had this 3D panel that we had built, and then we realized, like, wait, we can make this a separate node module. And so that's what we did. Tarek Solomon, who's the lead developer on MMGIS, been here since the beginning. He developed this whole node module called LithoSphere. Don't like to make mapping commercial names, but it's kind of like cesium, but different. Certainly a totally different way of doing 3D probably. But again, like we're using open formats, you can own your data. We support a lot of different cool things. We actually can support 3D tiles. But I don't say it's not going to be as awesome as cesium, but it gets you there in just terms of having an open source 3D viewer that you can plug in. Okay. The other thing we did for Lunar Viper, they wanted to show not only lines, but also the point, like the change in slope, let's say along a line. And you could have two data sets that are essentially replicative, aligns endpoints and do things like that. But we basically took GeoJSON. And an interesting thing about GeoJSON, you can actually, GeoJSON supports, an X, a Y, a Z, an M, right? A measurement. But it can also support, you can just stuff anything else in that coordinate field and it doesn't break the JSON. So we create what we call an enhanced JSON, where we each of the vector points along the line can have other attributes. And then we just have a separate property which says what those attributes are. And then MMGIS can go in and read those attributes and then do things like this hotline that you see at the bottom showing this is probably slope or something like that. So anyway, again, like expanding the format, but not breaking it, not necessarily creating a new format either, because we like to keep things open source. Another thing we did, DEM tiles, which are not necessarily unique in the geospatial world, but we have our version, which is where you're taking 30-bit floats and you're encoding them into the 4 bands of a PNG, of a ping. So then when we decode it, we can do things like change the elevation stretch on the fly. We can do the view shedding, which is this yellow you're seeing in the middle here. We can, create 3D on the fly. And that's how we do 3D in LithoSphere. We read these DEM tiles, and we take the corresponding visible tile, which becomes the texture for the mesh, and create those meshes on the fly. But this doesn't have to be elevation. It can be slope. It can be, spectral bands. It really doesn't matter. The other thing we've done is we've created what we call we time enabled MMGIS. But one of the things we also did was we made tiles time aware, and the only thing we did was just put the time into the folder structure name, and then MMGIS can actually scan through the folders on its machine and pull up the tiles that meet that time criteria. So at the bottom we have a timeline. And as we change it, we can get more and more tiles on the fly. And this is showing it actually somewhat real time. Its responsiveness. And we can either do a point in time if you have like data covering everywhere, or you can do a range. And actually, the other cool thing is that these tiles will actually self-mosaic on the fly. So if they overlap, they'll actually do the combination and put them together as a mosaic. And again, so we actually enabled time and vector layers and raster layers. So both are time sensitive, which was important for Lunar Viper, but we use it here on the Earth. Okay, I don't know how much time. Let me see. Okay, I've probably gone way over my time. But I'll try to wrap it up. So just, we have lots of other new features in terms of doing line of sight. The top left is actually demonstrating ability to do actually Elasticsearch queries for spatial data. A little bit on the top right there, some 3D things we did with continuous profiles and showing 3D models and things like that. Just move along. So because for Lunar Viper specifically, they wanted a lot of direct integration with their OpenMCT tool. And so we've actually added a lot of endpoints in terms of the configuration for adding and removing layers, touching vector layers, actually inputting vector data in real time on the fly into the application, and also adding and removing data from our draw tools and things like that. So lots of options for poking at MMGIS programmatically. And again, it got used on just a couple example missions that we used it on Mars helicopter. Was not expected because it was not supposed to last more than 5 flights, wound up being 72. And so we started incorporating telecom data, and we just used the M2020's deployment of MMGIS, which we call CAMP. Actually, the helicopter just used the same thing. So all we did was stick their data in. It was seamless, and allowed everyone, essentially to communicate or cross spacecraft at the very least. Again, so here's a little bit of example of Lunar Viper. I don't have demos because we give them the code and then they do their thing. But they are prepared and they've been testing it out. And so, we can actually connect to LunarServe, look at connect with a polar projection, and then they can actually feed data in real time. We've got webhooks to help connect databases, spatial databases to MMGIS and actually data to go back from MMGIS to them. Again, we've got real-time support and that expanded API. And JSC had used it early on to do some of their EVA planning and look at what it would take to have a map when you have astronauts on the ground, right? And do some testing, and actually built a little bit of a distance tool to kind of help play out how far a person could walk. Okay, yeah, and then emit, which I talked about. Okay, I think I'm just going to leave it there. And happy to take any questions.
Thank you, Phil, for this wonderful introduction and all the capabilities of MMGIS. And for now, we stop recording and then the discussion session starts.
Okay, thank you.